All right, good morning, everyone. Today we are taking on just a little bit more practice with Chapter 5.6, Normal Distributions Review. So here, what I want to make sure that everyone has out is our beautiful z-score chart. We will need it for our problem sets for today. All right, let me put that aside. Okay, so first up, find the area under a normal curve. Remember that the total area under any normal curve is going to be 1. I'm also saying write each statement using the inequality notation. So the absolute value of z is greater than a number, or its magnitude is greater than a number, or absolute value of z, its magnitude is less than a number. Okay, so here, find the area under the normal curve within 1.5 z-scores from the mean. So I always anchor myself right here. Here's my mean. I know that it's a z-score of 0. So I'm saying find the area within. So what does within imply, right? Well, if this is my mean and I go 1.5 z-scores above, let me mark that right here, and 1.5 below right here, we're saying, well, that distance is within 1.5 from the mean. So within really is saying in between. So we're trying to capture this area right here. And if I use my inequality notation to capture it, well, I'm saying that the distance from 0 has to be less than 1.5, right? My magnitude, my distance from 0 has to be less than 1.5. So as I move away from 0, now here, I'm exactly 1.5 z-scores away from the mean, and I want what's within it. I want whatever is less than that distance. So in my fancy notation, it would look like this. So absolute value of z is less than 1.5. I'm saying the magnitude is less than 1.5. Okay, now I have to solve it. So I'm going to go to my z-score chart and I'm going to look up a z-score of 1.5. And I want to find what is its area to the left. That's what my chart does, always to the left. So if I look up 1.5, there we go. So we see that the area, the proportion below is 0.9332. So 0.9332. And that is telling me this area below it. Okay, I'm going to also need this area, the proportion that's below a z-score of negative 1.5. So if I look at my z-score chart and I look at the negative 1.5, right here, I see, 0.0668. So 0.0668. So that's telling me this area right here. So to get that region that's in between them, I really just have to take that small away from the large. So I'm looking at what is 0.9332 minus 0.0668. And I end up with an area of 0.8664. I'm keeping the 4 decimal spots. I love precision. All right, next one, B. Find the area under the normal curve that is more than 1.5 z-scores away from the mean. So here again, I'm going to drop my anchor there at the mean, z-score of 0. I'm going to make a little marker here at a z-score of 1.5, and here, negative 1.5, because at those two extremes, we are 1.5 z-scores away from the mean. So if I want to be more than 1.5 away from the mean, I'm saying we're looking at the two tail regions here and here. And I just want to remind you that when I look up a z-score of negative 1.5 and I look at the area that's to the left, if I look at the z-score that has the same magnitude, so if this is negative 1.5, the z-score with the same magnitude would be 1.5, same distance from the mean, the area to the right here is going to be the same. These areas will match. So I really just have to find one of them, and I already did in the previous problem. So this area right here was 0.0668. This will be 2. So all I have to do is add them together, 0.0668, 0.0668, I get 0.1336 for the area. And if I write that in my fancy inequality notation, absolute value of z, or its magnitude, right, it has to be greater than 1.5 z-scores from the mean. So I would write it just like this. Okay, next up, what percent of a standard normal model is found in each region? So now I just want my answers to be percentages instead. So I'm looking at, well, what is the proportion that falls in this region? Okay, so here we're saying z is less than negative 1.9. So here is my mean, z-score of 0. Here is about a z-score of negative 1.9. So I keep giving you these normal curves just to help you visualize what it is that you're solving for, so you can see if your answer is appropriate or not, right? Sometimes it's helpful to see if your answer seems reasonable based on the space that you have shaded in the diagram. So here we're saying less than, so we're over in this little tail. This is our easiest variation because we can go straight to our z-score chart, look up that negative 1.9, and here is the area, the proportion that falls below. So 0.0287. But we're asked what percent falls in this region. So we'd say 2.87%. Okay, for B here, z is greater than 1.9. So here's my mean, a z-score of 0. And here is a z-score of 1.9. And it's saying greater than. Okay, so I need that area. So I know that when I use my chart, it's always giving me the proportion below. So I need to do 1 minus the proportion below. So if I look up a 1.9, 0.9713, I have to subtract it from 1. And I should end up with 0.0287 or 2.87%, right? It's exactly the same thing that we saw over here. So I just want to remind you that when I have z-scores that have the same magnitude, right, distance from the mean, and these are examples of z-scores with the same magnitude, the proportion to the left of the one that's negative and the proportion to the right of the one that's positive, always going to have the same area under the curve. Okay, for C. So for C here I'm saying, well, how about the proportion that's in between these two markers? So here again is my mean, z-score of 0. Here is my z-score of 1.9 about, and here is the negative 1.9. And we're saying, what about the in-between? So the in-between region, right, remember how we use our chart. If I look up a z-score of 1.9, it's going to give me the area, the proportion below it. Okay, and if I look up a z-score of negative 1.9, it gives me the area, the proportion below it. So once I have those two regions, I have to subtract the small from the large. So if I look up that z-score of 1.9, I actually already got it. That was the 0.9713 that we saw in part B. And then the proportion below the negative 1.9, we already saw that too in part A. So I'm taking away the 0.0287 from the 0.9713. And I'm left with 0.9426 or 94.26%. Okay, I can also visualize this one other way. Right here is my starting point. So here is that first area over in here. So that was the 0.9713. And then all I'm doing is I'm taking away this area that I'm highlighting right there. I hope that helps you to see it just a little bit more clearly. All right, the next one here, we're saying z is less than negative 1.9 or z is greater than 1.9. So here is my mean, a z-score of 0. So here is my 1.9, and over here is my negative 1.9. And we're saying, well, z could be less than negative 1.9, or it could be greater than 1.9. So I'm looking at those two tails, right? Those z-scores have the same magnitude, the same distance from the mean, right? It's 1.9 z-scores from the mean either way. So their areas, they have to match. And we already solved for them. So over here would be 0.0287. And over here would be 0.0287. So I just need to add those two regions. Gets me 0.0574, and then make it a percent. And there we go. So we get 5.74%. Okay, the last variations, right? I'm trying to give you every variation in this problem. So the last four on this page, notice how we see magnitudes. We see the absolute value notation. So here, this first one is saying absolute value of z is less than 2.3. So it's saying that the distance, the magnitude from the mean, where the z-score is 0, has to be less than 2.3. So here we're going to go ahead and I'm going to mark the mean of 0. And I'm going to write here about z-score of 2.3. So we're 2.3 standard deviations above the mean. And then over here, the z-score of about negative 2.3, right about there. Okay, so I'm looking at where is the distance from the mean less than 2.3 standard deviations. And that would be the in-between space right in here. Right, I could have also written that as negative 2.3 is less than z is less than 2.3. That's the region I'm really going after. And if I write this in words, I can say something like the distance from the mean, where the z-score is 0, is less than 2.3 standard deviations. Okay, so it's the in-between space one. So I need to look up a z-score of 2.3. So look up 2.3 on your chart. Look for the proportion that falls below it. We should see a 0.9893. Do the same thing for the negative 2.3. Okay, the proportion below would be 0.0107. So I'm looking at the area to the left here, the area to the left here, and I'm subtracting that small from the large. So 0.9893 minus 0.0107 is going to produce 0.9786, okay, or 97.86%. All right, the next one here, absolute value of z, magnitude, right, is less than negative 2.3. Well, can I have a distance that's less than something negative? That doesn't make a whole lot of sense to me. And if I go back to just this concept of absolute value, can I have a number that is being forced positive, right? These bars force it positive, that could be less than something negative? No matter what I plug in for z, say I try negative 10, 0, positive 10. No matter what I plug in, right, this will be always 0 or something positive. So I'm never going to get something that is less than something negative. So this one would be impossible. We'd have 0%. Let me remind you that a positive number cannot be less than a negative number. So 0%. All right, next one, absolute value of z, right? So the magnitude is greater than 2.3. So the distance from the mean, where the z-score is 0, is greater than 2.3 standard deviations. So my mean is right here. That's a z-score of 0. And here, again, the 2.3 marker. And here, the negative 2.3 marker. So we're saying, again, distance from mean is more than 2.3 standard deviations away. So as I move out from my mean, away from my mean, here I'm at 2.3, and here is the more. So I'm looking at the two tails again. And again, since they have the same magnitude, I know that their areas to the left here and to the right here, they're going to match. So if I wrote this in a simple inequality notation, this is like saying z is less than negative 2.3 or z is greater than positive 2.3. And if I write this in words, I can say the distance from the mean, where the z-score is 0, is greater than 2.3 standard deviations. So if I look up that z-score of negative 2.3, I already had that from the previous problem, I see that this area here is 0.0107, and this area will match. So I just have to add them. 0.0107 plus 0.0107, and I get 0.0214, or 2.14%. All right, last variation here. So absolute value of z, or its magnitude, is greater than negative 2.3. So its distance from the mean has to be greater than something negative. Well, isn't that always going to be true? No matter what I plug in here, that will always be true. A number that's forced positive will always be greater than something negative. So no matter what I plug in here for z, no matter what extreme value I plug in, it's going to be a true statement. So that really encompasses everything underneath my curve. 100% of it. So if I write this just in words, a positive number will always be more than a negative number. 100% is taken care of here. All right, so hopefully good just overview of all of the different variations of this particular skill. And now flip it over. We're going to do a few of the word type problems. All right, so here is my second page right here. So a little context. Okay, so a company that sells bags of gravel to construction companies has a machine that fills sacks with gravel. The weight of gravel in the sacks is assumed to have a normal distribution with a mean of 75 pounds and a standard deviation of 3 pounds. This low variation is important so that the customers feel satisfied with the product, which are advertised to contain 75 pounds of gravel. Sketch a picture of the normal curve below. So what they're saying is that variation is important for consistency. People want to make sure that they're getting, close to 75 pounds of gravel. Maybe a little bit more, maybe a little bit less, but it should be pretty close to that 75 that's promised on the packaging. So if I summarize this, I know that I can use this little notation, n parentheses, mean, comma, standard deviation. So in this problem, my mean is 75 pounds with a standard deviation of 3. Okay, I'm not going to make you draw this picture every time. I'm just trying to help you see what's happening. So my mean here would be 75 pounds, and my standard deviation is 3. So if I go up in increments of 3, here would be 78, here would be 81, here would be 84. Okay, over here would be 72, and then 69, and then 66. Okay, as a z-score, this would be 0, this would be 1, 2, 3, -1, -2, -3. So we remember that it's more usual, right? It's more typical to have values that cluster closer to the mean, and it's more atypical to have values that are far out in the tail region, right? It becomes more and more unusual the further out in the tails we are. All right, so here we're saying find the percent of bags that weigh less than 72.4 pounds. So I can visualize that I'm right in here, and I'm looking at the proportion that falls below it. Okay, so let's just remind you of the z-score formula as well. So z equals the observation minus the mean over the standard deviation. So that's our starting point. So let's find the z-score. So z equals the observation is 72.4 minus the mean over the standard deviation of 3. Okay, so when I type this into my calculator, I'm using a very basic z-score chart. So I'm going to the nearest tenth. It's one of the only times I have you round to the nearest tenth. So the z-score is about negative 0.9. So when I go to my z-score chart of negative 0.9, so right here, I'm seeing 0.1841. 0.1841. And then I'm just saying percent, find the percent of bags that we would expect to weigh less than 72.4 pounds. Well, that would be about 18.41%. All right, how about the percent of bags that weigh more than 79.7 pounds? So I'm looking somewhere in here, and I'm looking to the right because I'm looking at more than. So I have to start with my z-score. So z equals 79.7 minus the mean over the standard deviation. And when I type that in, I get about 1.6 when I'm rounding to the nearest tenth. So if I go to my z-score chart, I'm looking at 1.6. So here's my 1.6, 0.9452. But that gives me the proportion below. I want the above. I want the more than. So I do 1 minus 0.9452. So 1 minus 0.9452, and that gets me 0.0548, or 5.48%. Making sure everything is a percent. Right? We're looking really, like, what's the probability of this event playing out? Well, it has a 5.48% chance of playing out, of getting a bag that weighs more than 79.7 pounds. All right, find the percent of bags that weigh between 70 and 80 pounds. So here I have to find the two z-scores first. So z equals, I'll start with the 70 minus the mean over the standard deviation. So negative 1.7 z-score. Proportion below 0.0446. Okay, other z-score. Z equals 80 minus 75 over 3. Gets me about 1.7 or 0.9554. Okay, so here I have the z-scores. I have the proportion that falls below, and it's an in-between problem. So for the in-betweens, I take the bigger one, so 0.9554, right, the area to the left of a z-score of 1.7. So I'm looking at right here, I'm looking at the proportion below that z-score, and then I'm going to subtract the proportion below this z-score right here. So take away 0.0446, and I get 0.9108. So 91.08%. All right, lastly, our gravel company offers a money-back guarantee if the bags of gravel weigh less than 66 pounds. Right, we're shortchanging you so much, we're going to give you your money back. Okay, so we're looking at the proportion of bags that weigh less than 66 pounds. First and foremost, that's what we have to solve for. And then we're told if 5,000 bags are checked at random, right, a good quality control situation, how many bags would weigh less than 66 pounds and really be able to have that money back guarantee. So first, we're going after the z-score. So z equals 66 minus 75 divided by 3. And we get exactly -3, a z-score of -3. So we know, again, deeper out in the tail is very unusual. So this would be an unusual outcome, which is why it's offering that money-back guarantee. So if I look at the proportion below, a z-score of -3, it's really, really low. So right here, 0.0013. Okay, so that would be the proportion below a z-score of -3, or in this case, a bag of gravel that weighs 66 pounds. Okay, so now if I'm saying, well, 5,000 bags are checked, how many would we expect to weigh less than 66 pounds? Well, I'm just multiplying that by 5,000. So I'm taking the 0.0013, multiplying by 5,000, and we get 6.5. Okay, I can't have a portion of a bag, so I'm just following our normal rounding rules. Since we have 6.5, we're going to round up and say, oh, well, it's approximately 7 bags that would have that money back guarantee. All right, let's do one more word problem together. Let me slide this up. All right, example 4. So according to National Geographic, the average weight of a male grizzly bear is assumed to be normally distributed with a mean of 700 pounds and a standard deviation of 37 pounds. So let me summarize that off to the side. 700 pounds, pretty big. Standard deviation, 37. Okay, so then here I'm going to put the mean at 700. I'm going to add increments of 37. So I have 737, 774, and 811. And I'm going to take away increments of 37. So I have 663, 626, and 589. Here my z-score is 0. Here I'm plus 1, 2, 3, minus 1, minus 2, minus 3. Okay, so find the percent, so again, back to a percent of grizzly bears that weigh less than 650. So really what I have this example for is for you guys to practice independently. So once we're at this stage, maybe pause the video and see if you can answer these 4 questions. And when you're ready, you can unpause it and check it along with me. Okay, so the percent of grizzlies that weigh less than 650. Okay, so I have to find the z-score first. So I'm looking at the 650, that's my observation, minus my mean of 700, divided by my standard deviation of 37. So I get about 1.4, negative 1.4. So there's my z-score, negative 1.4. So if I go to my chart, right, the proportion below is 0.0808. So 8.08%. We'd expect 8.08% of male grizzlies to have a weight that's less than 650 pounds. Okay, find the percent of grizzlies that weigh more than 720 pounds. So again, z-score first. So z equals 720 minus 700 divided by 37. So I get about 0.5. So if I look at my z-score chart, it's going to give me an area of 0.6915. That is the proportion below. So I have to do 1 minus 0.6915 to get the proportion above, the more than. So I'm going to get 0.3085 or 30.85%. Okay, find the percent of grizzly bears that weigh between, so again, percent and an in between, 710 and 785. So I have to find the 2 z-scores. So if I focus on the 710, I have 710 minus 700 divided by 37. Gets me about 0.3. Okay, the area that goes with it, proportion below, 0.6179. Okay, my other z-score, 785 minus 700 over 37 is going to be about 2.3. So the proportion below would be 0.9893. Okay, so I have my 2 proportions below. So if I look at 785, that gives me the proportion that falls below here. And the, what's the other one, 710? So 710 right about here, that's the proportion below right there. So I need to take the big one, 0.9893, take away the smaller one, 0.6179, and that gets me 0.3714, or 37.14%. All right, last one. Let's say that grizzly bears are considered overweight. Poor grizzlies. If they weigh more than 800 pounds. If 1,500 grizzlies are checked at random, how many weigh more than 800 pounds? So first I have to find the proportion that weigh more than 800 pounds, and then I have to multiply by the 1,500. So first we go to the z-score chart. Right? First find the z-score, then go to the z-score chart. So z equals 800 minus 700 over 37. So the z-score is about 2.7. Okay, so again, we want more than 800 pounds. We know that the 800-pound marker is right here. We want the more than. So I need to do 1 minus the proportion below. So if I look at the 2.7, the proportion below is 0.9965. So we get 0.0035. That's our proportion that weigh more than 800 pounds. So now I take that number, the 0.0035, and I multiply by the 1,500 grizzlies, male grizzlies, and I get 5.25. That's what we would expect to see if we had a random sample of 1,500 grizzlies. So we can't have a portion of a grizzly, so I'm going to say round to the nearest grizzly bear. So we'd say this would be about 5 male grizzly bears. Box your answer, as always. All right, I hope this lecture made sense. I hope you guys are doing well.